Good morning, class. We are looking at practice test number 5, module 5, chapters 10, 11, and 12. Here's chapter 11, goodness of fit and contingency table. Goodness of fit test in multinomial experiments. Here are the observed frequencies from 4 categories, 5, 6, 8, and 13 at 0.05 significance level. Test the claim that the 4 categories are all equally likely, and everybody remembers the various steps in the test of hypothesis. We state the null and alternative hypothesis. What is the expected frequency for each of the 4 categories in this case? What is the value of test statistic, critical value, make a decision. So reminding everybody about the definition. A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed contribution. Goodness of fit hypothesis tests are always right-tailed if the sum of these weighted squares, chi-squared, is the summation of O minus E quantity squared over E. O is observed, is the expected value, is small. The observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from the distribution. Only when the sum is large is there reason to question the distribution. Therefore, the chi-square goodness of fit test is always the right-tail test. So we have more than 2 categories, and I want to remind you of binomial, which has 2 categories. In this case, we have more than 2. E is n over k, or E is n times p, the proportion, equals n over k, or summation of observed values over k. Summation of observed values is the n. In this case, 5, 6, 8, and 13 will be added and divided by however many. There are 4 categories. We end up with number 8 in this case. What is given? It's a multinomial experiment where k is 4. We have 4 different categories with the choice of alpha being 0.05. Therefore, we use a goodness of fit test. Also, each expected frequency, which is 8, does satisfy the requirement of being a value at least 5. That is the requirement. Because if expected account is less than 5, the result of chi-square test will not be accurate. So we're going to continue with the question. We are looking at the same question, and we are going to write step 1, H0, P1, P2, P3, P4. They're all the same, and that's the claim. And at least one of the probabilities or proportions is different, which makes it the right-tail test. The second step is to calculate the chi-squared value using the formula summation of O minus E quantity squared over E, which means 5 minus 8 quantity squared, 6 minus 8 quantity squared, 8 minus 8, 13 minus 8 quantity squared, add them up, divided by E, which is 8. That's the meaning of it. And we get 4.750. Critical value. Alpha is 0.05. Degrees of freedom is the number of categories, which happen to be 4, minus 1 is 3. And we can see from the table, this is the degrees of freedom. It's hard to see it perhaps, but the left column represents the degrees of freedom n minus 1. The top represents the alpha, and the answer is 7.815. Remember, this is the area to the right. Chi-square distribution is limited. And so with that being the case, we can look at the graph. This is the critical value. This is the test statistic way into the non-rejection region, and therefore we don't reject H0. That's really the concept. So if we are not rejecting H0, what are we rejecting? H1. And if we are not rejecting H0, we are not rejecting the claim either. The claim becomes true, and we restate the claim. There is sufficient evidence to support the claim that the four categories are all equally likely. So there is sufficient evidence for this claim. If we were to use a two-tailed test, then the chi-squared of the left would be 0.216, and the right one would be 9.348. And as you can see, this test statistic is between the two, which puts it in a non-rejection region. We get to the same decision. As far as technology is concerned, for example, you can use internet or the calculator. So we are going to edit and clear L1 and L2. In L1, we put the values. In L2, we give the expected value, which is the same for all of it. And we go with the chi-squared GOF, goodness of fit test. It picks up L1 and L2, or if you put it in a different lists, you can list them as follows. Degrees of freedom is K minus 1. You know it to be 3. And when you do the calculation, it does the calculation for you. So notice, this is the value of test statistic is done for us. This is the p-value. So p-value 0.19, let's say 1. It's way larger than alpha of 0.05. Therefore, fail to reject H0 or do not reject H0. That's the same. We're going to continue with a second question. A professor asked 40 of his students to identify the tire they would select as a flat tire of a car carrying 4 students who missed the test. An excuse. The following table summarizes the result. Use a 0.05 significance level to test the claim that all 4 tires have equal proportions of being claimed as flat, and we are going to use, I'm going to remind you of the formulas for chi-squared and E and so forth. And so left front 11, right front 15, and so forth. And I'm using LF to represent left front, lowercase rf to represent right front, and uppercase L, uppercase R to represent the left rear, lowercase r, uppercase R for the right rear, just to give you an idea. And first and foremost, we will add them up. 11 plus 15 plus 8 plus 6, they become 40. There are 4 categories divided by 4, or you can say 40 times 0.25, the proportion we are assuming equality, that means 0.25 or 25%. So the expected value is 10. So each expected frequency 10 does satisfy the requirement of being a value of at least 5. And we write H0 probability of all those tires, left front, right front, so on and so forth, they're the same. And that is the claim. And at least one of the proportions is not equal to 0.25, or they are not equal, which makes it a two-tailed test. However, as I mentioned, for the restriction, we go with the right-hand test. I will show you the result for the two-tailed test as well, but we will always treat that as a right-tailed test. And so we calculate the test statistic using this formula, the observed minus the expected. So 11 minus 10 squared plus 15 minus 10 squared plus 8 minus 10 squared plus 6 minus 10 squared. And we divide it by E, which is 10, according to this formula, resulting in 4.6. That's the value of test statistic. Critical value comes from the choice of alpha. Degrees of freedom is k minus 1 or 3. And we've seen it in the previous pages, the same value, chi-squared equals 7.815. So this is the value of critical value. Test statistic is smaller than that, way into the non-rejection region. Do not reject H0. When you don't reject H0, then you don't reject the claim, which becomes true, and you restate. There is sufficient evidence to support the claim that all four tires have equal proportions of being claimed as flat. If by any chance we go with the two-tailed test, the two values are 0.216 and 9.348, and again, this number, test statistic is in between, everybody, between non-rejection region. So when four students identify the flat tire, it is not likely for all to select the same tire. Test of independence. Using a 0.05 significance level, test a claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or a girl. And here's the information. Here's the table that is giving us the information here. So how many men survived? 332. Women, boys, girls. How many died? That's the given information. Let's add them up and find the total for each column. These two numbers, 1692, these two numbers, 422, and so on. Let's go with the total as far as the rows are concerned in the same manner. So adding up those four numbers results in 706, those four numbers 15, 17. So when you add these two numbers or these four numbers, you must get the same answer, and it's 22, 23. The expected frequency is defined as the row sum times the column sum divided by the grand total. So use the formula to find expected frequencies for the upper left-hand cell. Specifically, I'll show you the work for one of them and the rest of them repeat. Ultimately, you do this with technology, but to see how it's calculated. So if I want to use this number and find its expected value, I multiply the row sum, which is this number, by the column sum, which is this number, and then I divide by, this is called the grand total. Okay. So 1692 and 706, the product of the two divided by 22, 23. So 706 times 1692 divided by that. And that's an expectation, although that refers to the number of people, but we're going to keep it with decimals, okay? And so if we do this calculation for each one, and it's tedious, we can write the expected value for each case. So using the same procedure, the table of expected values become this. So this is the actual value, this is the expected value, so on and so forth. So specifically for this one, it's been calculated as such. Now, interpretation. What does it mean? And this is important to interpret the result for this upper left corner, for this one, left-hand cell. Although 332 men survived, we would have expected E equals 537.36 men to survive if survivability is independent of whether the person is a man, woman, boy, or girl. There is a discrepancy between this observed value of 332 and this expected value of 537.36, and such discrepancies are key components of the test statistic that is a collective measure of the overall disagreement between the observed frequencies and the frequencies expected with independent between the row and column variables. Here's another example. To interpret this result for the lower left-hand cell, we can say although O is 1360, so look at this one. 1360 men actually died. If survivability is independent of whether the person is a man or woman, there should be an expected value of 1,154.60 for men that should have died instead. That would be the meaning of this. Note, a summation of E in rows and columns are consistent. So as these numbers work out, if you do the expected value, they also work out row-wise and column-wise. And if there is a discrepancy, maybe like 0.01 or something like that due to round-off error. But if you add these two numbers, you get 1692. If you add these two numbers, the same thing, these two numbers, the same thing, these two numbers, the same thing. Now, let's again continue with the discussion and then we will solve that problem. Contingency table. Let's look at definitions. A contingency table or two-way frequency table is a table consisting of frequency counts of categorical data corresponding to two different variables. One variable is used to categorize rows and a second variable is used to categorize columns. When data can be tabulated in table form in terms of frequency, several types of hypotheses can be tested by using the chi-square test. Chi-square test, test of independence of variables. In a test of independence, we test the null hypothesis that is contingency table. The row and column variables are independent. That is, there is no dependency between the row variable and the column variable. You might say there is no dependency or there is no relation. The test of independence of variable is used to determine whether two variables are independent or independent of or related to each other when a single sample is selected. So test of the independence deals with a single sample. Test of independence are always right-tail test. If the sum of this weighted square deviation is small, the observed frequencies are close to expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is a reason to question the distribution. Therefore, the test of independence always right-tail test. So continuing with the same question we've been doing, we've done some of the calculations. First and foremost, the requirements. We're going to assume random selection results of the or frequencies and expected value is way larger than 5, as you know. So here's how we write H0 and H1. H0, whether a person survived is independent of whether the person is a man, woman, or boy, or a girl. Or you could write the row variable is independent of the column variable. That means that's a general case for each independent case, and that's the claim. Surviving the Titanic and being a man, woman, boy, or girl is dependent. Or you can say the row variable is dependent or related to the column variable, and it makes it a right-tail test. So With that being the case, let's calculate this. Again, the process normally is done by technology, but just to give you an idea how this thing observed minus expected divided by expected. So 332 minus 537.36 squared divided by 537.36 plus 318 minus 134.022 squared divided by 134.022. And the last one, so in this manner, the last one is 18 minus this number 30.709 squared over 30.709. Remember, in the previous case, all expected values were the same. This is not the case here. That's why you want to be careful when you do the calculation. We end up with a huge value as far as the test statistic is concerned. The next step is to find the critical value, which is depending on the choice of alpha, which is 0.05, and degrees of freedom, which is r minus 1 times c minus 1. Okay, so we have two rows, 2 minus 1 is 1, 1, 2, 3, 4 columns, 4 minus 1. So please don't mix up the total. Those are not part of rows and columns that we calculate here. 2 minus 1 times 4 minus 1 is 3, and we get to 7.815. And just by the sheer value of the test statistic, which is way into the rejection region, you're going to reject H0, and the rest of them works, obviously. So you are going to reject H0. That means you're rejecting the claim. That means you're rejecting independency. So the claim becomes false. And there is not sufficient evidence to support the claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or a girl, or in short, survival and gender are dependent. That's the same thing as saying what we just did. Now, we can do by technology. So first and foremost, we need a matrix. And so, for example, in TI, second and x to the power of -1, that will give us the access to the matrix. We first put the size 2 by 4. I don't have enough room, but it shows, for example, this is 332, this is 1360, this is 318, this is 104, this is 29, this is 35, and there's not enough room to show the rest of it. But if you push the arrow, you can see that when you're doing the work. So first, we enter the matrix in A. Then we go with tests, and we use chi-squared test. So stat test, chi-squared test. And when we do chi-squared test, it picks up the A and B matrices. If you put that in A, what happens the B will be the expected. It will calculate it for you. You don't have to do anything. Just continue with the calculation. Notice number 1, and you continue, you see that one. If you put the B, notice this is the value of chi-squared that you've calculated. This is the p-value. The p-value, I mean, the p-value is the area to the right of this number. It's 0. It is practically 0, which is clearly less than alpha of 0.05, and you get to the same result, rejecting H0. So the p-value from the chi-squared is 0. If you were to use the table, would be the same thing. Okay, highest value than 12.838, and the p-value is less than 0.05. This is now what I want you to notice is the expected frequency. Notice the B matrix. If you look it up, look at this value, 537.36. Look at this value. This value that you calculated is here. Look at the bottom, 1154.63.64, right? And the next one and the next one. There's not enough room to show the whole thing, but you get the picture, and this means arrow go to the right. So the expected one, the expected values are automatically calculated and put into the B matrix. P value is 0, less than alpha, reject H0. All right, test of homogeneity. Using the following table with the alpha of 0.05 significance level, test the claim. Test the effect of poster gender on survey responses by men. So we have men who agree, men who disagree, and the gender of interviewer is men versus women, so the results are different. So, chi-square test of homogeneity. Test of homogeneity of proportions is a test of the claim that different populations have the same proportion of some characteristic. The test of homogeneity of proportion is used to determine whether the proportion for a variable are equal when several samples are selected from different populations. Test of homogeneity are right-tailed. If the sum of this weighted square deviation is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that came from the distribution. Only when the sum is large, the reason to question the distribution. Therefore, the test of homogeneity is always right-tailed test. So we do the total again. We add these two numbers, we add these two numbers. We do the total here, we add these two numbers, we add these two numbers. And so the idea is that we want to find the expected value, and we do exactly the same manner. To find the expected frequency, row sum times column sum divided by grand total. So for example, okay, this is the table of expected value. So for example, if I want for 560, I'm going to multiply these two and divide it by this number. Okay, so it's done. Okay, so 560. I'm going to multiply 868 by 800 divided by 1200, and I get this value. So just as an example, to show one means you know how to calculate. Requirements. Based on the description of the study, we will treat the subjects as being randomly selected and randomly assigned to different posters. The results are expressed as frequency counts. The expected frequencies are all at least 5. If so, the counts will be approximately normally distributed. That's the idea. So we're going to continue with this question. Again, this is the information from the previous page, and H0, the proportion of agree-disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. In other words, P1, P2, P3, however many. Now, one way to write that, you can say survey responses by men are independent of poster gender. That's it. Again, you don't have to write both of them, but you need to understand this means this. And that's the claim. What is H1? The proportions are different. At least one proportion is different from the others, or corresponding to this one. Survey responses by men depend on poster gender, which makes it a right-tail test. And we're going to go with that. So for example, the first cell, 560 minus 578.67 squared divided by this number. And you do the same thing here, plus 308 minus 289.33 squared over 289.33 all the way to the last. And you calculate this again. You don't have to do this by hand. I've shown you can use, a calculator, and the answer is 6.529. Degrees of freedom. We have 2 columns, 2 rows. So 2 minus 1, 2 minus 1 gives you 1 with the alpha of 0.05. So you have one, and if you go with the table, you get 3.841. And if you go with the graph, you can see that this is the critical value, and the uh, test statistic is way into the rejection region. You're going to reject H0, which means you are rejecting independence, and the claim becomes false, and you rewrite it. There are various ways of rewriting it. I want to go over that. There is not sufficient evidence to support the claim that the proportion of agree-disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. That's one way to write it. There is sufficient evidence to reject the claim of equal proportion. I wanted to write that because I've seen various ways of writing, so you want to be exposed to that. Finally, a different way of saying the same thing. Survey responses by men depend on pollster gender. Now, if you go with the two-tailed test, by the way, this number is way larger than the chi-squared of the right. And again, it puts you in the rejection region and you get to the same decision. Take a look at those two values. All right, test of homogeneity using the following table with a 0.05 significance level. Test the association between people living in a city and becoming infected with a highly resistant bacteria. So we have bacterial condition, infected, non-infected. Living location could be city, outside city. So we have those values. And again, we're going to go through the process. H0, whether a person is infected, is independent of whether the person lives in the city or outside the city, or they have the same proportion, and that's the claim. Whether a person is infected is dependent of whether the person lives in the city or outside the city, which makes it a right-tailed test. Now, this is the test statistic, and to calculate this, I'm going to show you again the same formula that we have here. We have to calculate the total here, the total here, the total here, the total here, and here's the grand total. So total of each column, total of each row, and the grand total. That means these two numbers or these two numbers or these four numbers. These four numbers gives you the green one. And so E is that. And again, as an example, if I want to do it for this one, I'm going to multiply these two numbers and divide it by the grand total. So if I can do one, I can do all. And here's the table that represents the expected frequency for each of those cells. There are four cells. There are four cells here. And also, you can calculate individually the difference between this and this, square it and divide by this. So you can put that into this table, O minus E quantity squared divided by E individually. And now if you add them up is the answer here. Okay, so add them up is the answer here, or just show it. Either way is fine. I want to show you that if you were to do it, for example, with Excel, perhaps you calculate this with the simple formula, and you're ready to move on. The degrees of freedom is 1 because you have two columns, two rows, 2 minus 1, 2 minus 1. The product is 1, alpha is 0.05, so you get the chi-squared of 3.841. And if you go with this graph, you can see that the test statistic is way larger than the critical value, which puts us way into the rejection region. Therefore, we reject H0. As far as the technology is concerned, by the way, this can be, and it's done, this one is done by Excel. And look at the information here, class. For example, this value is test statistic. It's calculated here. Here's the critical value. Okay. And here's the p-value, which is less than alpha of 0.05, and therefore you reject H0. So here's the decision making. Okay. So reject H0. reject H0. Oh, the order was wrong. There is not sufficient, so reject H0, the claim becomes false. There is not sufficient evidence to support the claim that whether a person is infected is independent of whether the person lives in the city or outside the city. Another way of writing it. Whether a person is infected is dependent of whether the person lives in the city or outside the city. So it depends where you live. That's the bottom line. And again, if you look at the p-value from here, this number compared to alpha, that gives you the same decision, everybody.